welcome back. This is the second half of week 1 lecture on limits and continuity. So let me kind of show you the animation here to start. So we want to talk about what it means for a function to be continuous. You've seen this in pre-calculus. The kind of intuitive definition is that a function is continuous if you can draw it with your pen without lifting your pen. But here's a more formal definition. A function is continuous at a number a. So again, this is continuity at one point. So if at x is a, if the limit as x approach a is equal to the function defined at a. So there's a few things here we want to point out. So this definition is equivalent to saying three things. The first is that the function has to be defined. So if I plug in a into f, it has to give me a number. Second thing is the limit has to exist. And we've seen this before. The limit in the last lecture is as x approach a from the left and from the right, it has to be the same number. It has to be well defined. And then lastly, 1 and 2 must be the same. In other words, the limit and the function has to agree. And so those are the three things that imply in this definition. Again, the function is defined, the limit exists, and they are the same. So let's kind of see some examples here. Okay, so this is kind of a generic example to kind of see what does it mean for a function to be continuous. So first of all, you see that there's a few points here that the function is not continuous, right? So the first part is that on the left here, when x is 1, there's a hole, so that's definitely not continuous. More on removable a little later. And then here there's a jump in the middle at x is 3. And then at x is 5, there's a hole, and then there's also a dot above the hole, the red dot there. So between 1 and 5, 1, right, the function is not even defined at 1. There's no dot anywhere. Whereas at 5, at least there's a dot, but the dot, notice, is not where the hole is, right? And so these are the three places where the function is not continuous, and let's kind of see why based on the definition. So for example, why is 1 not continuous? Well, the function is not even defined. If I plug in 1 into f, there's no value. So remember in the earlier definition we said that if, let's go back here a little bit, the function has to be defined at a. If it's not defined, if it's a hole, then it cannot be continuous. And so that's the first problem with x being 1. The function is not defined. And then how about at 3? Well, the problem is that the limit, right? Notice that if I take the limit as x approach 3 from the left, is something different than the limit as x approach 3 from the right. So that means the limit does not exist, right? The limit from left and right is not the same, so the limit is undefined. So that's why this point is not continuous. How about at 5? 5 is really close. It's actually the closest of the three to being continuous. The limit does exist, right? If I approach from the left and the right, it's the same. The limit exists. But the problem is that, and the function is defined as well. Unlike when x is 1, the function is not defined. When x is 5, the function is defined. The problem is that the limit and the function does not agree. And that's why this is also not continuous. So there's the animation there for y at x is 4, it is continuous, right? The limit, notice in the animation here, the limit exists. As I approach from both sides, it approaches the same point. And the green point there, the function defined there, and the function is defined and is equal to the limit. So that's why x is 4 is continuous. Okay, let's look at some algebraic example. Here are four functions that we want to look at. And we want to kind of see which of these functions is discontinuous and where. Okay, the first one, let's analyze that carefully. You have a rational function. First of all, how do I graph this? Well, this is a little bit tricky, but if I can do some factoring and cancellation, turns out this is actually pretty clear how to graph this. If I will factor the numerator, and then notice there's a cancellation here. So as long as x is not 2, which is not in the domain of the function, then this is not 0, and we can make a cancellation. So this function is actually equal to this function after the cancellation, as long as x is not 2. Again, when x is 2, the original function is not the same thing as this x plus 1 simplified form when x is 2, because 2 is undefined. But as long as x is not 2, the rational function above is the same as this linear function, this equation of a line, as long as x is not 2. So that means that when I'm able to graph it, right, notice that as long as x is not 2, the line here is the same as the rational function above. So everywhere else is just a line. So they're exactly the same. Except when x is 2, it's a hole, because when x is 2, right, the original function is undefined. So there's a hole at x plus is equal to 2. So notice this is the case where we have that it's not continuous, but you know, the first case we saw earlier, this is the removable case where the function, the limit exists, but it's just a hole there. So that means that in part A, the function is continuous everywhere. The only place where it's not continuous is when x is 2. So f is undefined. Is actually that's a typo there. Actually no, it's not a typo. So let me clarify that. So yeah, the function is undefined. Therefore, it makes it discontinuous. Okay, how about this one? Notice this is the exact same function, right? But earlier we have a hole that is undefined. So now we're going to fix that by defining. When x is 2, we're going to make a definition and make the function be 1. So notice, right, when x is 2, we make the dot at 1. Earlier in the part A, there was not even a dot anywhere. So automatically the function is discontinuous. But now let's see if we give it a dot. If we give it a dot by defining at 1, at least the function is defined now. So the function is defined. If f of 2 is 1, the limit does exist. Notice the limit is 3, right? As I approach it from either side of 2, the limit is 3. So the limit exists, the function is defined, but the problem is that the limit and the function do not agree. The limit is 3, the function defined at 1, right? Defined being 1 at x is 2, they're not the same. So this is also not continuous when x is 2, but it is continuous everywhere else, like before. This case, everywhere is okay except at 0. So the function is defined at 0 to be 1, but the problem is that the function everywhere else blow up at 0 going to infinity. So the function is defined, but the limit is infinity, which is not a number, so that limit it does not exist. So therefore, because the limit and the function is not the same, this is also discontinuous. Again, only at 0, right? At 0, when x is 0, the function is not continuous, but everywhere else, the function is continuous. And then the last example, part D, you might remember this as the greatest integer function. So this means that this double bracket means that the output is the greatest integer that is less than or equal to x. So for example, what is the greatest integer less than or equal to 1.5? Right here. So look at my mouse. If I'm at 1.5, the biggest integer less than or equal to 1.5 is 1. If I look at 1.1, the greatest integer less than or equal to 1.1 is also 1. So really anywhere between 1 and 2, the biggest integer less than or equal to that is the value right before um, right before that integer. So give me 1 second. Sorry about that. My alarm just went off there. Sorry. Um, okay, now notice that. So let's do another example here. If I put in 2.1, the biggest integer less than or equal to 2.1 is 2. So we see this is a step function. It jumps at integer. At every integer point, it jumps up by 1. And so the function is continuous everywhere, right? Except for at the integer points. 1, 2, 3, 4, 0, -1, -2. All those points, the limit from the left and the limit from the right is not the same. There's a jump. So the function has a bunch of, actually an infinite number of places where it's not continuous, namely all the integer points. All these jumps, the function is not continuous. But between the jumps, the function is continuous. Okay, so and then the last thing here is that I want to talk about this theorem called the intermediate value theorem. This sounds kind of complicated here, but it's actually really simple. If you have a function that's continuous on a closed interval, and suppose that there's a value n that is between the output f of a and the output f of b, if n is between those values, and let's say the f of a and f of b is not the same, then this theorem guarantees that there is a c somewhere between a and b such that f of c is that n value. Again, n could be any number between f of a and f of b. And this function guarantees that the function will attain that value at some point between f of a and f of b. Okay, let's kind of give you a picture. I think this theorem is very simple if I look at a picture. So for example, here the function, here you have a function. Again, we assume it's continuous. F of a is here. Here's the height f of a. Here's the height f of b. Right? And so if I pick any point n, n could be anywhere between f of a and f of b. N is anywhere between these two values. So look at my cursor here. N is any value here. And the theorem, the intermediate value theorem, guarantees that the function must attain all n value between f of a and f of b. In other words, the function has to go between f of a and f of b. It has to cross every single value from f of a and f of b. It cannot have any jump discontinuity. It cannot jump anywhere between f of a and f of b because the function is continuous. So in other words, if n is any value, so let's pick a random value here between f of a and f of b, then the function has to cross it somewhere, right? Cross it right here. The function guarantees that there is a point somewhere between a and b such that the function cross that value at n. So here it is. So here's the value that in this case, this input will give you that output n. And this is true for any n between f of a and f of b. So here the n here is attained at least once. The theorem guarantees that the function will cross n at least once. Again, if I move n up and down here, the function has to cross every value. So you cannot jump over any value between f of a and f of b. Here's another example. So notice that here let's kind of go back a little bit here. Is that again the theorem guarantees that there's a c such that f of c is n, and so there's that c right there. F of c is n. Now here's another example. The function guarantees that the theorem guarantees that it crosses at least once, but it can do it more than once. So for example, here's a continuous function. N is this value. Notice that in this case, the function actually crosses n 3 times, right? Here at C1, again at C2, and at C3 as well. So the function really crosses n. The theorem guarantees that crosses n at least one time, and sometimes it can cross it more than one time. So that's the intermediate value theorem. It has actually a few applications, but we'll talk about a couple here. So for example, let's look at a function here. This function, here's a function on the left. We want to know whether this equation has a solution, has a root in the interval between 1 and 2. In other words, is there an x value between 1 and 2 such that when you plug it in here, you get 0? Or in other words, can I solve this equation finding a solution and the solution is between 1 and 2? Well, first of all, this function is continuous. It's a polynomial, and so let's look at the value of. Let's plug in some value here. Let's plug in 1 and 2 and see what happens. If I plug in 1, notice I get -1, which is a negative value. If I plug in 2, I get a positive value. So the theorem says that because f of 1 is negative and f of 2 is positive, the theorem guarantees that the function must go through every value between the red dot and the green dot. In particular, 0 is between those two y value, so that the function has to go through 0, right? Again, we don't know what it looks like, but the function has to go through 0 at least once. And that's exactly the c, such that f of c is 0. So that means that we know there's at least one solution. There's at least a c between 1 and 2 such that the function is 0, meaning the equation here has a solution. So that's an example of how to apply the intermediate value theorem. Okay, I want to go back to the slide here and kind of we covered all these cases here from the slide, but I want to kind of give you some more definition. So earlier we said that the function is continuous if the limit is equal to the function. Another definition that we want to talk about is that a function can be continuous at a point from the right and from the left of a point. So a function is continuous from the right if when x approaches a from the right, this plus means from the right, if the limit as x approaches a from the right is equal to f of a. And then a function is continuous from the left at a if the limit from the left is equal to the function. And so the example we saw earlier, which is the greatest integer function, is a good example of this. So let me go back to that. So if we look at the here, again, we saw earlier that this function is not continuous at 1, 2, 3, and at any other integer point. But notice that this function is continuous if I look at from the left or from the right. One of them will be continuous. So for example, what is the limit as x approaches 1 from the right, from the plus side? The limit as x approaches 1 from the right is 1. Notice that the limit is equal to the function. The dot is equal to the limit from the right. So that means that this function is continuous from the right, but is not continuous from the left. What's the limit as x approaches 1 from the left? Or x approaches 1, with the negative sign. So if x approaches 1 from the left, the limit is 0, right? But the function is 1. So there's a jump there. So it's not continuous from the left, but it is continuous from the right. Same thing here at 2. The function, the f of 2 is 2. The limit from the right is also 2. So the limit from the right equals the function. So the function is continuous from the right side, but it's not continuous from the left side, because if I take the limit from the left, the limit is 1, but the function is jumps. So the limit from the left does not equal the function, therefore it's not continuous from the left. And then a function is continuous on the entire interval if it's continuous everywhere in that interval, including at the endpoint from the left and from the right. And then this is an example of just an algebraic way of checking to see if a function is continuous. This is where you just do limits, really. So if I take the limit, so notice in this interval from -1 to 1, if I take the limit as x approach any point between -1 and 1, we can, this is a simple function where you can actually plug it in. So you really can plug it in. If I plug any point from -1 to 1, the limit, we saw earlier, if I plug it in and the function is well defined there, then the limit and the function is the same. Therefore, this function is continuous everywhere in the interval, including at the endpoint. If I take the limit from the right side of -1 and or the left side of +1, the limit and the function is the same, so therefore it's continuous everywhere. So here's a picture of that, right? Again, if anywhere here the limit is equal to the function, including the endpoint. Notice from the endpoint, the limit from the right is equal to the function for -1, and at 1 the limit from the left is equal to the function. So this function is continuous everywhere between -1 and +1. And in general, when you have continuous function, you can add them and the function is still continuous at those points. The product, the difference, right? You multiply a continuous function by a scalar, even dividing, as long as the denominator at a is not 0, then all of these operations preserve continuity. You have two functions that are continuous at a, adding, subtracting, multiplying, dividing, again as long as the denominator is not 0, and even multiply it by a constant c, all those keep the function being continuous at a. Polynomials, right? All polynomials are continuous. All rational functions are continuous as long as the denominator is not 0. So here's a rational function. Again, we saw an example of this earlier. As long as the denominator is not 0, in fact, the denominator is 0 exactly when x is 5/3. So as long as x is not 5/3, then this function is continuous everywhere except for 5/3, the place where the denominator is 0. And that's from this theorem, right? Rational functions continuous everywhere as long as the denominator is not 0. So polynomials, rational function, right? Root function, trig function, inverse trig function, exponential function, log function, all the functions we learned from pre-calculus, as long as you're in the domain of those functions, then the function is continuous on the domain. And then when you have functions and you compose them with composition, so if f and g are continuous and you compose them, then the composition is also continuous. So for example, x squared is continuous, sine is continuous, so when you compose them, it's continuous. And then 1 plus cosine is continuous. Again, ln is continuous when in the domain. In other words, it's continuous as long as the input here is positive. Then when you compose them, again, only look in the domain that we have continuity. So for example, all the places where cosine is -1, if cosine is -1, that makes this inside 0. Natural log is not defined at 0. So 0 is not the domain of the natural log. So the only place where it's not continuous is at the places where cosine is -1. So at these places, right, we have these vertical asymptotes. So as long as it's not those places, as long as you're in the domain, this f of x here is continuous. And then the intermediate value theorem we just saw earlier, we had the animation that describes this on Manim. And then I think we also covered this example as well in the Manim animation a little bit earlier. And then last thing is that we have to be careful with the intermediate value theorem. Maybe one more thing I'll say is that this intermediate value theorem only works if the function is continuous. Right? If the function is not continuous, so for example 1 over x is not continuous at 0, so you cannot apply the intermediate value theorem. You cannot say that, the function is negative on the left, positive on the right, so it must go through 0. This one doesn't. It actually jumps it jump across 0. Because the function is not continuous, you don't guarantee that the function crosses every value. So you want to be careful when you apply the intermediate value theorem. Okay, and then one last example is that how do you make a piecewise function continuous? You have two pieces. There's a parabola on the left of 1, and then on the right of 1, you have a linear function. How do you make sure that the function is continuous everywhere? Well, the only place where we're not sure about is 1, because 1 is where you piece them together. When you piece them together, it's possible that they may have a jump for this piecewise function. So for this to be continuous, at 1, the place where you piece them together, you have to make sure the limit from the left on this function and the limit from the right on this function, they have to agree. And they have to agree to the function at 1. So again, that's the definition of continuity. This right here is the definition of continuity. The limit from the left at 1 and the limit approaching 1 from the right, this is the plus symbol, has to be equal to the function defined at 1. Again, that's the first definition we saw at the beginning of this lecture. So for this to work, we have to make sure the algebra works out. So if x approaches 1 from the left, if you're on the left of 1, you're on the line. So that limit is simple because, if you're on the left side of 1, you're on the parabola. So if I'm approaching 1 from the left, I'm on the parabola, and this is a polynomial, so it's continuous. So you can plug in 1, and you get, plug in 1 for x, and you get 1 plus k. So the limit from the left is 1 plus k. The limit from the right, if you're on the right side of this function, then you are on the line, 3x. So the limit as x approaches 1 from the right, again, you plug in 1 into the line, you get 3. So that means that you need both 1 plus k, the left limit, and the right limit, 3, they have to be the same. And also, what's f of 1? If you plug in f of 1, you look at this right here, you get 3. f of 1 is 3. So that means that we need all of these 3 to be equal to 3. The function is 3, so the limit has to be 3 as well. So the limit on the right is already 3, so we're done there. But the limit on the left, we need k to be 2, so that we do have, if k is 2, then the limit from the left is 3, and then everything works out. And so the only way for this to be continuous is k has to be 2. If k is not 2, there's going to be a jump here. So again, notice from this function here, notice before 1, when x is less than 1, that you have a parabola. But notice this is very subtle. After 1, you have a line. See how this is a straight line right here. So you're piecing a line with a parabola, and the only way for this to be continuous is that if k is 2, then the parabola and the line meet exactly at the same spot, and we have continuity. But if k is not 2, then you might have a jump here, right? You might have a gap here that makes it not continuous. Okay, that's it for this lecture. Okay, thanks for watching.